Thank you very much. I'll start by thanking the organizers for this opportunity and this great conference. It's wonderful to be back, and I believe the last time I was on this side of the conference was 6 years ago in Dublin. So anyway, it's good to be back. The story I want to tell today is about the big picture of the workflow that we do in quantum field theory and some of the challenges, what's difficult, what makes perturbation theory difficult, what kinds of things come out of it, and ways in which we can improve the general toolbox and the general workflow. Let's see. Okay. So I wanted to start actually with something like phenomenological approach, which is what are the things that come out of quantum field theory in the loop expansion? Well, whether it be a number or a function of observable data, like a scattering amplitude, we have the loop expansion, which is a perturbative expansion in H bar. And we all learn in quantum field theory class that we just sum up all the Feynman diagrams, do all the integrals, and we're done. So the essential work of a quantum field theorist is just really 2 steps, pretty easy. Sum all the diagrams, do all the integrals. That's it. Now, there are a few caveats here. First of all, and I'm speaking for myself here, often we are not interested in actual observables, but something closely related to an actual observable, such as something like a scattering amplitude for massless particles, which is not really an observable. So we're often, it's worth bearing in mind that we're often comfortable talking about things that are not necessarily finite in whatever dimensions our quantum field theory is defined. And that does come up, a lot, causes some issues. Okay, so what comes out of this machinery? Well, from the loop when we do the loop integrals at L loops, we get some power of pi, which just comes from the volume of the spherical integral there. And then we get some objective weight, and I'm putting it in quotes. I want to define that actually sharply later on in this talk, but I know this is a somewhat controversial word from the mathematical point of view, an objective weight that has bounded weight, whatever that means. And as a phenomenologist, let's just look at the data and see what comes out. I don't really need to review this so much for us here, but we can, any calculation that people have done to high orders, what kinds of numbers come out? Well, we can look in the gyromagnetic ratio, and we see some unusual numbers here: pi squared, log 2, zeta 3, which is the natural logarithm evaluated at the number 1. And for the even zeta values, we have nice formulas for these in terms of Bernoulli numbers. And zeta 3, we can think about it this way. It's nice to have a name for a number like this. There's value in having a symbol that everybody recognizes that you can type into your computer and get as many digits as you want. When we write an expression like this, it's essentially infinite precision, because what we mean by that is that these symbols all make sense on everybody's computer, and we can get them to as many digits as we want. Well, we can go to 3 loops, and we have a similar expression. But interestingly, there is no infinite precision formula expression known at 4 loops. And part of the reason is because there are numbers that appear in this that have been calculated to tens of thousands of digits that do not have names. And because we don't have names for them, and because Mathematica doesn't know what they are, we don't have an infinite precision bet. And this is something that is a recurring bottleneck and a challenge to overcome out of the output of quantum field theory. But we can look around in other theories, say scalar phi-4 theory. And luckily, conveniently for me, there's a paper by Oliver Schnetz, which is numbers and functions in quantum field theory. What comes out of it? And you can just do a survey. And sure enough, all these, you find zeta values. So zeta is evaluated at various numbers, multi-zeta values, some unusual things like P77, which is some weird combination of stuff. But you'll notice, and importantly right here, there's a caveat. This list is incomplete at loop 8 order. And indeed, there's a sense that every example you know of is a polylogarithm or pi's and logs evaluated at some numbers, like maybe the 4th polylogarithm evaluated at 1/2, which occurs in the gyromagnetic ratio at 3 loops. But we now know that these things, oh, let's look at our favorite quantum field theory. In n equals 4 in the planar limit, one of the simplest numbers we can calculate is the cusp anomalous dimensions, or what I say simplest, what I mean is one of the most elementary non-functions that we can calculate to pretty high order, especially using integrability, is the cusp anomalous dimension, which has this beautiful expression in terms of zeta values, where the product of every single term has a fixed transcendental weight. This has a normal meaning, and it has integer coefficients, sums of products of zeta values with integer coefficients. Now, partly based on this and many other examples that people had, there was an idea that in planar maximally supersymmetric Yang-Mills that the theory would be maximally transcendental, that there wouldn't be rational numbers sitting around. And this is very closely related to the idea that this particular quantum field theory would be entirely determined by its leading singularities. Now, these are two claims that I believe I've fluctuated about in my career, and I would say strongly that I believe that both of these are true, but with important qualifications. In particular, the meaning of transcendental has changed quite a bit, or has evolved, and also the meaning of what leading singularities are has changed. So I believe that this is true, but with a lot of qualifications, or we've learned a lot. But partly from examples like this, and also some general theoretical input, this was even formalized as a conjecture that the output of a quantum field theory, or at least in phi 4 or in certain categories, Kontsevich had conjectured that multi-zeta values would be, he actually conjectured there would be mixed Tate type, which then Brown and Schnetz proved would imply there would be multi-zeta values. But we now know that there be dragons, more complicated things arise. And that is one of the problems, difficulties in quantum field theory, but it's not the biggest one. And I don't think that's our biggest challenge today, but it's definitely a huge one. What functions appear? So what are the kinds of functions? Well, this object of weight, that I would have said many years ago that it was probably some algebraic on-shell kind of function, like a tree amplitude or something, and then some pure transcendental function of a given weight, bounded by this degree. At one loop, what are these functions that come out at L loops? Well, it's a general theorem that at one loop in any quantum field theory, any scalar integral will give you a iterated polylogarithm. And this is very conveniently a class of functions which we as a community in the last 20 years have really mastered and understand a great deal about their analytic structure and how to use them and work with them. And they include all the zeta values, all the examples we've seen. So this is a very general, very broad class of functions that we understand extremely well. And in terms of these prefactors, these algebraic pieces that are not transcendental, the best category that we understand are these products of on-shell amplitudes glued together, the generalizations of unitarity cuts that I'll come back to in a little bit, that are defined nicely in a gauge invariant way for all quantum field theories, and we can calculate. And in some quantum field theories, like massless theories in 4 dimensions, there's a beautiful correspondence between this vocabulary of functions and certain volumes in the Grassmannian. And in the case of planar, maximally supersymmetric Yang-Mills, the entire theory becomes combinatorial. And there are even nice formulas about how many different linearly independent on-shell prefactors there might be for a given process. However, even this notion has to change, or at least what the meaning of algebraic has to change slightly, I believe, because we now know that this, at least a strict meaning of algebraic, as an algebraic function of the kinematics, cannot be true. We know that there are a broader class of prefactors that are required to represent scattering amplitudes. And the first example of this we explored in a work with Mark Spradlin and my students. And this, interestingly, it's an elliptic integral. It's a complete elliptic integral divided by pi. So you might call that weight 0, but it's certainly not an algebraic function in the normal sense of it, but it is Yangian invariant. It's beautiful, but we don't know how to categorize these things, these different kinds of periods. There needs to be a richer thing, and we do not understand yet the classification of this, even this side of this, let alone the other side, these products. Okay, going back to our just 2 steps. As everybody I think in this room knows, Well, actually, I don't know. What is the hardest work of quantum field theory? I think for a long time, people would have said the summing Feynman diagrams is hard. It was explosively large. We've gotten very good at that, and I'll have more to say about this. But I think for the last several decades, by far, the hardest part to converting this series expansion into actual numbers for experiments has been doing the integrals. And this is what I've been focusing my attention on for the last many years and what I want to talk mostly about today. But it's worth pausing and stepping back, I guess, and saying, why is loop integration so hard? What is it? We can open up a textbook, and it's kind of funny. I want to take our kind of textbook approach and just kind of, maybe look at it again from a different point of view. So we start off with a loop integral, which is some integral over Minkowski space to, L copies of Minkowski space. And the first thing we learn is we don't know how to do those integrals. And so we introduce Feynman parameters, and we change it into a different integral. We take this product of factors, and we turn it into this, raised to some power. And this makes the loop integral part trivial, because it makes it spherically symmetric. And then we're left over with an integral over Feynman parameters. Unfortunately, we don't know how to do these integrals either. And so if you are, but maybe you can put this on a computer and get digits, maybe. And if you, learn more sophisticated tricks, and especially, which by the way, are very powerful in cases where there are very few scaling dimensions, when there are very few scales involved in the problem, you learn a trick to, you re-express the second semantic in terms of the independent kinematic parameters here, and you don't know how to do this integral, so you introduce Mellon-Barnes parameters, and you transform this integral into you use the Barnes lemma, or this kind of trivial identity, to convert this over to now an integral over Mellon-Barnes parameters, which again, I just want to point out, we don't know how to do. Okay. However, if there are very few kinematic parameters, this can have extremely good numerical convergence. And conveniently for real experiments in the real world, very few processes of relevance to experiments involve many, many scales. So this is a very good effective technique for, say, applications relevant to LHC. But as somebody who's interested in the general case, this is not especially, I've just changed one thing to another that I still don't understand, going from one to the other. And it can, of course, be very good for numerical convergence. But this is our standard pathway. And at what point have we finished? It's worth looking at a concrete example of this whole strategy. So take this box integral. It's an 8-point function in 5-4 theory, or it's equivalently just the tree amplitude in scalar 5-4 theory, massless scalar 5-4 theory in position space. So it's a very simple little integral. And you can introduce Feynman parameters, write it this way. You can do one of the Feynman parametric integrals pretty easily, and you get this nice rational function of two kinematic cross ratios, or cross ratios of the 4 points that define the integral. And Semantic did this integral in 1972 and wrote it using Mellon-Barnes parameters as a relatively compact thing, manifestly a function of u and v. And this, from the from the picture of the Barnes expansion, you can get a very good series expansion at small u or small v from this. And of course, you can put this on a computer. But of course, you still have a two-dimensional integral. You have a two-dimensional integral, two-dimensional integral. And I think the answer that most people in this room would probably agree of being the final answer would be the formula roughly given by Hodges in 1977, where you have polylogarithms. This is a classical polylogarithm of weight 2 of these functions, of algebraic functions of these cross ratios here. And why is it that we think this is the final answer? Well, for one thing, we understand these functions extremely well. For another, I can put that on the computer and I can get as many digits out as I'd like to essentially arbitrary precision. But it is worth bearing in mind that the symbol Li2 is just defined as a series expansion or as an integral. So as formally speaking, the meaning of these symbols is the same as a two-dimensional integral like this, a rational integral, sure enough. But why is it that we prefer this symbol over this symbol or this symbol? And which one should we count as the real integral? Anyway, we can look beyond and see what kinds of, why these things are scary. If we go to higher multiplicity in position space in 5-4 theory, you can look at this 8-point function, and you find that, or sorry, 6-point function, and this is a weight 3 polylogarithm, but an integral over some elliptic curve. And as you keep going, you find a scarier and scarier class of functions. This is in a holomorphic volume form over an elliptically fibered K3. These are classes of integrals that we do not understand anywhere near as well, although there's been enormous progress. And I should probably do a better job of acknowledging all of the great progress, especially on the elliptic polylogarithm case, of generalizing the tools of symbology and the other technology that we have developed for understanding polylogarithms. Our understanding of the analytic structure of these functions is so severely lacking that we can't even hope to play the games like Lance's game with the bootstrap, where you don't even need to sum the Feynman diagrams. You just know the analytic structures of the class of functions that can come out, and you can just lock it down knowing consistency conditions. We're light years away from doing that. Here, we don't understand their branch structure. We don't understand their analytic structure. We don't understand their functional identities. This is a very big math problem, and it's one that is too big for me. So I'm not going to have much more to say about this in the rest of this talk. But this is a big looming challenge to our understanding of the output of quantum field theory, is that there's a class of functions that we need, which we don't have the kinds of technology that we have now for polylogarithms. Okay. So in terms of these two steps, well, broadly speaking, the way I would like to improve this is by improving the work we've done to understand summing Feynman diagrams is very closely related to the work we need to do the Feynman integrals. And the idea, broadly speaking, is to improve this challenging problem of loop integration by finding better forms of loop integrands. And I just want to talk a little bit about the loop integrands, although that's not really the primary focus today. But we, as a community, have gotten tremendously good at computing loop integrands, because they are the sums of Feynman diagrams. And basically the same ideas and the same tricks that we have for that led to the beautiful formulas for tree amplitudes, like BCFW recursion, work just as well for loop integrands and give you relatively compact, very concrete expressions for loop integrands. There's a nice geometric picture, which I'm not going to talk about at all, but you can interpret these as triangulating the amplituhedron. And we've, as a community, have almost, we've gotten so good at understanding the generation of the loop integrands that this is almost not even a problem today, except that these very powerful tools that give you expressions very quickly and very compactly give you an expression that is almost hopeless from the point of view of doing the loop integrals. And to give you an idea of why, so I want to explain this kind of briefly. Someday we might understand how to do these integrals, but at the moment the output of recursion relations is so far from anything that we can use that it's almost a non-starter. So the general form that comes out, the analogs of the spurious poles that come out of BCFW for tree level, are spurious propagators at loop level. And unfortunately, those spurious propagators can involve arbitrarily high degree polynomials in the loop momenta. Now, this is a class of functions that none of those techniques that I showed you, that flowchart of, introduce Feynman parameters, introduce Mellon, none of those techniques work. So, and that's even setting aside the fact that these integrals are usually divergent. So none of the tools that we have that we understand how to take a Feynman integral and convert it to a number or a function that we know how to name work for this class of integrals, even when you can avoid, even when you're not concerned with issues about finiteness. So this, someday we might know how to do these integrals, but we're pretty far from that today. So far, in fact, that it's worth going back to where this whole story started, I think, or at least these pictures and the origins of the recursion relations have their origins in understanding how to compute things more directly in terms of integrals that we do know how to do. And there's a classic result by 't Hooft and Veltman that at one loop you can express any something in d dimensions in terms of scalar integrals with at most d propagators. This is a very famous thing that everybody, I think, understands. And we can think about this basis as a basis for cohomology, for loop integrand cohomology. And that actually has an asterisk for an important reason, because it is absolutely not a master integral basis by the normal sense, in the sense of differential forms modulo integration by parts identities. What is, strictly speaking, the scalar integrals form a subspace of the master integrals, which do not integrate to zero. Or said another way, all other differential forms can be chosen so that they integrate to zero, and then only things left are these scalar pgons. So it is a basis for the non-vanishing part of the master integrals. Okay, and you can find these coefficients by IBP reduction. And just as we've heard about in some of the talks this week, there's very efficient code that takes Feynman diagrams, individual Feynman graphs, and spits it out in terms of this basis of master integrals using Laporta's algorithm, et cetera. And one of the great insights that I think led to all of the revolutions going on in scattering amplitudes, one of the original gems here, was the idea that you didn't need to use IBP reduction to calculate these coefficients. What you could do, in fact, you could compute these directly, not diagram by diagram, but for a scattering amplitude, you could compute them directly in terms of on-shell data. And at one loop, you could calculate it in terms of trees. And this is under the general umbrella of generalized unitarity. The idea is relatively simple. You can compute, say, this unitarity cut. And on the left-hand side and on the right-hand side, you know what your basis integrals do here. And you know what the amplitude does there. These are sums of all the graphs of this topology. This is a tree, and so you get the sum of Feynman diagrams. And this is something you can recursively compute in terms of on-shell tree amplitudes involving fewer loop momenta. And that is where these pictures first emerged. And today, we do not yet know how to do this very well out beyond one loop in a general quantum field theory. But this is something that we're getting better at here. Today, I think if you go to the state of the art in most phenomenological applications, they're literally taking Feynman diagrams and doing IBP reduction term by term and then trying to collect it. But there should be something like generalized unitarity that gives you directly this expression, these coefficients directly in terms of gauge invariant, meaningful scattering amplitude data. So the way this works more generally, and it's a relatively simple, big picture, the devil's in the details, is that if you suppose you want to calculate some scattering amplitude at L loops, you choose a basis for cohomology, a set of master integrands. Maybe modulo integrating to zero, although people usually ignore that beyond one loop. They usually mean a literal basis for cohomology. And the point is that to find these coefficients, we can compute periods of both sides in terms of on-shell data. So this is what I'm calling the method of generalized unitarity. The idea is that you for each integrand, there exists some integration cycle, a dual element of homology, and you can compute this period matrix, which is independent of loop momenta because you've integrated it all out. So this is matching, and there exists a set of cycles for your masters, which gives you a full rank matrix. Now, provided that every one of these integration cycles involves cutting at least two propagators, which is always possible, thanks to a theorem by Andrej, then you can compute every one of these. The left-hand side you can compute in terms of lower loop on-shell gauge invariant data. Now, one of the things we've learned is that these cycles, these integration cycles, cannot just include contours around simple poles, the residues of propagators. You also need to compute things like K3 cycles and other things. But broadly speaking, I can compute the left-hand side on every one of these cycles in terms of on-shell data. The right-hand side, I just compute for my basis. And then I just simply invert that matrix to determine all the coefficients. So that's how we do this. Good luck. But it does allow us to reproduce perturbation theory without reference to the Feynman expansion. Okay. Oh, nine. Okay, so we can see how this works. We can take the famous Park-Taylor example, and at tree level, it's just times one. And at one loop, there were famous results by the same gentleman discovered this, story that at one loop, this amplitude is given just by the sum of two mass easy boxes, the so-called two mass easy boxes, or maybe that and one mass, depending on how you define that, which is connected to the no triangle hypothesis related to the good ultraviolet behavior of this theory in the planar limit. And so in terms of the basis of masters that were given to us by Passarino and Veltman, or 't Hooft and Veltman, we know that we don't need the triangles or the bubbles. We'll come back to that in a little bit. I think you might want them, but that only the boxes are required, and you get a nice expression. But as soon as you get to two loops, the problem of finding a set of master integrals turns out to be a much bigger, much broader, open-ended problem. And at two loops, the two loops generalization of this was first achieved in 2009 by Christian Burgu, who chose a basis of masters, computed all these cuts, determined all the coefficients for arbitrary multiplicity. And the answer was this 12-page formula where the masters are chosen here, or the particular coefficients. And this is the generalization of that, of just the two mass easy boxes. Now, of course, the problem with this story so far is that whenever you're choosing a basis of masters and finding the coefficients, the beauty of your answer depends on the choice of your basis. And there's some art in finding a good basis. Are these good masters or not? I don't know. Well, within a few months of this, my collaborators and I guessed this formula at two loops, and we were able to push that up to three loops. But these formulas were guessed and checked. Now, they were kind of built out of nice Feynman-like integrals. These wavy lines mean particular loop-dependent numerators. And it turns out that these integrals that we guessed satisfy nice differential equations. They were engineered to be very nice-like integrals. And indeed, they turn out to be very nice. But this was mostly guesswork. And what's happened in the intervening years is that this simplicity, or the existence of or the ability to construct a basis of masters which are engineered to match the cuts of field theory one by one, is possible for all renormalizable quantum field theories to arbitrary loop order. So there's a relatively straightforward systematic procedure for constructing a set of master integrands for any scattering amplitude in any quantum field theory, a loop order, as long as it's renormalizable. Power counting is bounded. Okay, but that still leaves the question. What about doing the integrals? Well, I've known Lance for a very long time, and this has always been the big challenge for my career here. So the idea, the insight, I think, about the generalized unitarity, or this use of master integrands, is that it allows you to decide what is a good integral. And if you find a nice integral, any integral, independent of your quantum field theory in question, a Feynman-like integral that is nice, meaning that you know how to do it, pick it as a master. It should be one of your masters. You can study an integral now independent of any particular quantum field theory and choose it to be a particular master's. The most common choice that is used that forms the foundation for all of our vocabulary of most applications are these scalar integrals raised to various analytically continued exponents in dim-reg. Now, this is a very nice, convenient basis. Not only is it obvious, but it's a general theorem that these integrals are meromorphic in the exponents and in epsilon, with simple poles only occurring at integers. There's a lot of very nice theorems, and this is a space of masters that we understand quite well. And moreover, they're extremely well implemented code that will project onto this choice of doing the IBP reduction in the space of these integrals is very efficient. But you might ask, are these nice integrals? And at one loop, kind of, and at two loops, absolutely not. These are about the worst things. And in fact, it is safe to say that beyond one loop, these integrals are so hard that virtually none of them are known. These are almost impossibly difficult as integrals because they're just terrible integrals. They're absolutely terrible. And a lot of the art, and I'm going to come back to that, what we actually do today when we talk about doing loop integrals is actually to construct good integrals that we can actually integrate one by one. So the general observation is that we get to choose our master integrands. And clearly the choice that we make is going to affect the beauty of our answer and the efficiency with which we can calculate, use it. And why not spend some time thinking about what are the best integrands? And this brings me back to this one loop box. What do we consider a nice function to be? Do we consider this? This is literally the result of scalar integral here of the 1 over these 4 propagators. You get this particular transcendental function with a certain prefactor. And I would like to say that, and this is generally true, that at any one loop integral, Feynman integral, scalar Feynman integral, will give you some Gramian times a sum of weight of fixed weight polylogarithms, like this. And the terms in the parentheses are very nice. They're so nice that people have been scaling out this prefactor for a long time. It's very natural to scale it out. But there's a very technical and important reason why the terms in the parentheses are better than the product. And that is that when you differentiate log, you get a lower weight polylog. It goes down in weight, that there's a grading. And if I keep differentiating down, I'll get to rational. Whereas if I differentiate the scalar integral, I get the product rule. So I get a homogeneous term at the same weight and then a sum of lower weight. So there's a definite preference here for pure integrals. And by the meaning of purity here is that they satisfy canonical differential equations. What are the differential equations, by the way? When I differentiate with respect to u of I, not of the product, but of I just get logs and logs. These things should be viewed. The image of the derivative of this integral should be considered a master integral of lower weight. It is usually not. I'll come back to that. But surely these are nicer integrals. And if you differentiate them again, you'll get constants. Oh. So this was formalized by Johannes a few years ago in the methods of differential equations, and is now, my understanding is that it's essentially the state of the art. This is the gold standard for doing integrals today. Is you start off with any choice of master integrals, and then you rearrange them so that they satisfy this property, that they satisfy nilpotent differential equations. And the idea there, and this is a formal definition of weight as good as any other, which is that what I mean by transcendental weight is that there exists a substrata of master integrals that I'm going to call at weight L minus 1, with the property that when I differentiate with respect to their parameters, I get something of lower weight, necessarily lower weight. If that is true, then I'm going to call that the transcendental weight. And this system of differential equations is a very powerful way of actually doing the integrals. Because once you have a system of differential equations like this, it can be iterated. You can integrate it up iteratively, and it gives you a very efficient way of understanding these things. Interestingly, it rarely gives you a nice closed formula in terms of polylogarithms, but it is something that is very effective. And this is today more or less the gold standard for how when you have done these integrals. And the statement that the scalar integrals of raised to various exponents are bad is that they are extremely far from this property, and you need to take weird linear combinations to get to a canonical choice. But once you have a canonical basis, then you project into it. But my complaint, and what I want to spend the last bit of my talk on, is complaining that this is a relatively weak requirement. And I think we can construct better choices of bases. Because, of course, if you have a canonical basis, any linear combination with constant coefficients is another canonical basis. That's perfectly fine. And yet, that can be a dense rotation, a dense, consider a giant, if your basis is size k, you have a dense k by k matrix of rational numbers. It can make a huge difference on how pretty the answer is. And it can have a huge effect on your understanding of the physics connected to these bases. And what I want to encourage you, and what I've been spending most of my energy thinking about, is how to choose master integrals so that they are pure and that they are specifically tailored to capture certain aspects of quantum field theory that are important to us. Okay. So at one loop, purity is so simple. I mean, basically, the statement is that a scalar integral is proportional to something that's pure. So whether or not you include it almost makes no difference. It doesn't really affect our ability to do the integrals, as we know, because these integrals have been tabulated in appendices of papers for decades. They're relatively easy to do, unlike at two loops, where almost none of them are known. At one loop, we just kind of write them down and we have them. And part of that is probably because they're almost pure. But I want to complain that even at one loop, they are unnecessarily bad. They are bad choices for a lot of reasons. And some of this connects with what Ruth was talking about earlier about having these spurious symbol letters that cancel out in sums and identities about the infrared structure. And it's relatively easy to see. For example, in the space of one loop, let's say we're going to do in 4 dimensions. So I care about boxes, triangles, bubbles, and tadpoles, and the constant maybe. In DimReg, almost all of the 2 mass easy boxes that we write down for, say, the MHV amplitude are infrared divergent. But they are all unnecessarily infrared divergent in the sense that there are regions in loop momentum space where they're infrared divergent is when you are soft and or collinear at one of these massless corners. And that means that that's associated with a triangle subtopology. And so in the space of scalar P-gon integrals, you can just subtract out all of the scalar triangles that are responsible for the divergent regions of this integral and thereby define a finite box. This linear combinations of boxes and triangles is manifestly infrared finite, absolutely perfectly free of infrared finiteness. Now, of course, this spoils dual conformal invariance, okay? But it's a perfectly valid basis, and it's just a very simple rotation. But now, instead of having divergences sprinkled around throughout every single scalar box, you can subtract off the divergence of any scalar box can be removed by removing a triangle subtopology. And similarly, in the current, people are very comfortable with a bunch of triangles, bubbles, and boxes. In that basis, we're a little overly comfortable with just having a bubble integral as a master, which is ultraviolet divergent. Why would we do that? Why is it when I ask Fire to give me the derivative of a finite box integral, it expands it as a sum of a linear combination of 4 different ultraviolet divergent integrals? Why? If it's finite, and especially if it's conformal, shouldn't I get it directly as a conformal thing? Shouldn't we choose our masters to have that property? And indeed, it's actually pretty trivial. If you can choose any bubble to be your ultraviolet divergent master integral, and then subtract it from every other bubble, and now every bubble is finite. I'm excluding the 0 mass bubbles, which are infrared and UV divergent. But for the massive bubbles, at least, the difference of any 2 bubbles is just trivially a log ratio of 2 scales, perfectly finite in 4 dimensions. And so by just doing these subtractions to take bubble differences instead of bubbles, and so removing triangle subtopologies from your boxes, you can render an enormous fraction of your basis manifestly ultraviolet and UV finite. And I want to compare this. So say you're at 7 particles, every single box integrals you have is IR divergent because there are no massive boxes. But by removing their triangle subtopologies, all of them are finite, okay? There are 7 finite triangle integrals, and there's 28 infrared divergent triangles. You can't do anything about the infrared divergences of triangles. Those are real, so they're not associated with subtopologies. So you're going to keep those there. But in the bubbles, instead of having 7, which are UV and IR divergent, and 14, or n choose 2 total, but all of them are UV divergent, you can make one of them UV divergent, one of them UV and IR divergent, and all the rest can be rendered finite, perfectly UV and IR finite. And when you do this simple rotation in the basis, what do you find? Now, you can't just have the answer be the sum of 2 mass easy boxes, because that, first of all, the finite boxes are finite. The answer has to now include also divergent triangles. And what you find is that the coefficient of every one of those divergent triangles is exactly the tree. And if you remove the UV divergences from all of your bubbles except for one, the coefficient of that UV divergent bubble is the tree. And now the entire rest of your basis is finite in 4 dimensions, perfectly finite in 4D. That means I don't need to care about order epsilon corrections to the coefficients, nothing. This is a trick that works at L loops. You can just systematically remove the unnecessary divergences from these integrals and thereby render almost all of your basis finite. And I think when you do this, you discover that say the one-mass triangles have a lot of spurious letters. All of those cancel out. They're not present because the amplitudes do not have support in regions of infrared divergence that are collinear, that are not soft collinear. Anyway, and you can do this at any points. And I just encourage you, this is almost so trivial, but it is a very valuable lesson that can be reused at higher loops. And if you do this for in n equals, to do non-supersymmetric Yang mills, you need to expand this basis of integrals. It's also, you need to have mu to the fourth times boxes and mu squared times bubbles. So you need a slightly broader class, but at least for n equals 1 supersymmetry, this is an extremely effective basis to write down the answer, where the UV divergence is manifestly proportional to the tree and the infrared divergence are manifestly universal and proportional to the tree. Everything else is finite. Okay, so I guess this is kind of where I want to end here, is that when we construct our master integrals, not only should we choose ones that are good, meaning that we can do the integrals, meaning they satisfy canonical differential equations, that they're nice, but we should divide up our masters according to structure that we care about as physicists, like dividing them up into finite ones and divergent ones. And if an integral is entirely divergent because of a contact term, remove it. You know, it's very simple policy. And in that basis, the finiteness, the finite observables will be much more manifest, if not entirely so. But you can even divide it better. You can talk about UV divergent versus IR divergent. You can talk about degree of divergence. This starts happening at two loops where you have, you know, the UV divergence squared versus UV divergence to the single power. And you can divide up your basis to capture individual orders in the epsilon expansion or in the log M expansion if you have a IR regulator. But we can do this even better. We can also divide it up by weight. We carve it out by things at certain strata of weight. And we can also order it by rigidity, which we've been able to do successfully at two loops, where we can construct. So a typical scalar pentabox at two loops is a sum of 4 different elliptic polylogarithms and a polylogarithm. It's a big nightmare of a mess. That's why nobody knows how to do those integrals. But it is possible to associate with, to remove support from these subtopologies and construct a basis for which every master integral is a pure weight 4 polylogarithm or a pure elliptic polylogarithm of the same weight. Pure, again, meaning satisfies canonical differential equations, and where there's exactly one elliptic topology associated with every master. I don't yet know if this is the best. I don't know if that's the best, but those bases exist. We should try to construct them. And this is closely connected to a lot of bottlenecks. I can't remember what exactly Ruth had in her slide. I think it was something simplicity and I forgot, but this is the same sentiment here. This, I guess I want to close on this kind of virtuous cycle of scattering amplitudes. Somebody does compute something very difficult and we discover simplicity. Once we scratch our head for a while, and once we understand it, we can feed this back in to extend our computational reach even further. And as long as we're talking about general properties of amplitudes or about the mathematical structure underlying these things, the applications include everything that quantum field theory is used for, from the LHC to gravitational wave astronomy to early universe cosmology and lots of interesting mathematics. Thank you very much.